So this is the diode conduction state tutorial sheet solution, and in question 1 I'm only going to do the solutions where I've given the answers in the tutorial sheet, so that you'll get some practice of some of the questions which you don't know the answers to. And the reason for that is that the question is in 2 parts, and if I give you the answer you'll know what to choose in the first part to get to the answer most quickly. And that's not really the idea of the sheet. So the first question I'm going to do is 1b, and the circuit in question is a battery of 4 volts in series with a resistor of 3.9 kiloohms, in series with a diode, in series with a 6-volt battery. And the question wants us to find out if the diode is conducting, and if it is, to find out what the current that it carries is, and if it's not, to find out what the reverse bias voltage is. So either it's conducting or it's not, and we have to choose. And the best thing to do is to say, well, I'm going to work out what the voltages are around the diode, assuming that it's not conducting. So we can say, well, look, if the diode is not conducting, I can replace it with an open circuit. So if I replace the diode with an open circuit, I'll end up with this. And I can say, well, if there is this one loop now, I've got 6 volts here, because I've got the 6-volt battery, and I've got 4 volts here, and I can't have any current in here. That must be 0, because there is no pathway for the current to flow. If current's flowing here, it must be going down there, and if it's going down there, it's got to be going along there, which means it must be going up there, which means it gets to here, but now there's a break. So if there's current here, it means there must be current in the whole loop. And since there is no complete closed circuit, there is no current. So if there's no current in the 39 kiloohm resistor, we can apply Ohm's law, which is I times R. Well, if that's 0, it doesn't matter how big that is, this must be 0 as well. So there is no voltage across there. Now, if you wanted to, you could draw that arrow the other way round and say that the current flows that way, or the current that would flows that way, and that this arrow was like that. It's entirely up to you. And the way that you write down the equations, this problem is, to my mind, relatively simple, so I probably won't be writing out any equations for it. But if you were in a situation where you needed to write out some equations to solve the problem, the algebra that you write out will deal with your choices of arrow direction for you, as long as you obey all the signs properly. So as long as your maths is consistent, you don't have to worry about your choices of voltage and current directions. It will sort itself out. Right, so in that case we can work out what the voltage difference is across this gap here. We've got 6 volts on this point, and we've got 4 volts on this point, and there's no extra voltage across there, so this must be 4 volts as well, which means I've got 2 volts there, and that's plus, because 6 is more than 4. As I said, no equations. So if that's the case, then our diode, which we've taken out and replaced it with an open circuit, has 2 volts across it, and if it's a silicon diode, and the question says that it is, and the question also goes on to say that you can assume that the turn-on voltage of your diode is 0.7 volts, and if you reach 0.7 volts, you may assume that the diode switches on immediately and conducts any current that the circuit will permit it to. So in terms of our diode model, we had some diode models, and one of them was, this is VA anode to cathode, and this is anode current. We had one model that was, if I say 0 volts is here, and this is minus a couple, just to bring it off the axis. We had one model that was reverse bias, nothing, 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 turn on immediately. And we had another one that was at 0.7 volts, turn on immediately, and before 0.7 volts, nothing's going on at all. And then we had another one that said there was nothing up to 0.7 volts, and then the current increased as a straight line, and this line is representing the series resistance. Yeah, right on the wall. Series resistance. So for the purposes of this tutorial sheet and the questions that you might meet in your practice or in an exam, we'll be worried about that model there. Turns on at 0.7 volts and has no series resistance at all. So in that case we can move on from this point and say, well, we know that the diode must be conducting now because 2 is more than 0.7. So I can get rid of all my green and red. And we can say that, I'll redraw the circuit bit. And say, well, I know now that this diode is switched on. And I know that once it's switched on, whatever I do to it, its voltage will never increase above 0.7 because the line that I had drawn over there went straight up. That's to say, however much current it conducts, no more voltage. So I know that's going to be 0.7. And I know that this is still 6 volts because it's there. So that means that this point here, with respect to this point here, this is our reference, this big bit here, this is our reference. So this node with respect to that node, so I could draw that as that voltage there if I wanted to, is going to be 6 minus 0.7, which is 5.3. And I know that this is 4 volts because it's there. So that means I can do that less that, and I'll get the voltage that is across the resistor. And it's 1.3 volts, which is 5.3 minus 4. 5.3 minus 4. So if I've got 1.3 volts across a resistor whose resistance is 3.9 kiloohms, I can say, well, applying Ohm's law, I'll have I is V upon R, and we can say, well, then we've got 1.3 volts and 3.9 kiloohms. So, because I've got volts in kiloohms, my answer will be in milliamps. If you want to, you can say 3,900 ohms and get an answer in amps. Entirely up to you. Anyway, so 1.3 volts, 3.9 kiloohms will leave us with 333 microamps. And that is our complete solution for that question. And with a bit of luck, it does match what it says on the answers. It's good when that happens. So that's question 1B. Question 1C I won't do because there is no answer given. So, I'm sorry, question 1C I won't do because there's no answer given. And question 1D has a constant current source of 1 milliamp in parallel with a resistance of value 1.5 kiloohms. in parallel with a diode. Right then. So we know that the current's going to have to be going this way, and that it will be going down there, and the current's going to be shared out potentially, possibly, between these two branches, the resistor and the diode. Now, the resistor's quite happy with current in any direction, it's not too bothered, but the diode gets very sad about current the wrong way. It doesn't want to let any current through if it's reverse biased, so we'll have to decide what's going to happen. If we assume that the diode's open circuit for a bit, so we'll take the diode away and we'll worry about the resistor and the current source. So, no diode. Current goes up there, down there again. In that case, because the resistor dissipates power, the current and voltage must be in opposite directions to each other. It's in lecture 1 or lecture 2. So I know, having drawn the current source, how it is in the question with the current going down the page, and the current goes round this loop, that I must draw the voltage this way. If I don't, I've broken some laws, and what I'd be saying in that breaking of laws is that the resistor is giving energy to the circuit, and that isn't the case. Sources have their current and voltage in the same direction. Dissipators don't. Resistors are dissipators, and voltage and current sources are sources. And you can have a source of power as well if you wished. Perfect inductors and perfect capacitors do not dissipate any power, although real inductors and real capacitors do dissipate power. So we've got a milliamp and 1.5 kiloohms, so V is I times R, V is 1 times 10 raised minus 3 times 1.5 times 10 raised 3. That cancels, so I've got 1.5 volts. If you don't fancy that, you can do 1 and 1.5, same answers. So 1.5 volts here. Okay, well, if we remember which way our diode was, it was this way. So if I did put that diode in the circuit, because the diode and the resistor are in parallel, whatever voltage I've got just here, I'm going to have it here as well, because this is one conducting pathway. There's no extra resistances in here or anything, it's a perfect conductor. So that means that I've got my cathode, that one, at 1.5 volts greater potential than my anode. Well, that means it's reverse biased, because just as this point and this point are connected together, so this point and this point are connected together. So this diode is reverse biased. Its cathode at a greater potential than its anode, and if you look at the IV characteristic, wow, that's bad. If you look at the IV characteristic of the diode, we have, this is voltage anode to cathode, and this is the positive bit and this is the negative bit. So this is going to be 0 and this is going to be minus and this is going to be plus, and we'll have 0.7 about there. So in forward bias, nothing, turn on, and for our resistance and diode in series, we've got a straight line, and for our diode without any resistance, we've got, sorry, the straight line with the gradient, we've got the straight line without a gradient. But for all this business here, all this reverse bias, we can just assume that it goes on forever and ever and ever. It will never ever break down. Of course, in the lectures that we've been going through, I talked about impact ionisation briefly, and I said how the diode will eventually break down. But for the purposes of these questions, it's not necessary to worry about it, and we can just say it's reverse biased, there is no current, not even a saturation current. So the answer to this question is our assumption about the diode being non-conducting or switched off was correct, and this is where we stop. We've got our answer, 1.5 volts reverse biased. Part E, or question 1, part E, is also gives a solution in the sheet, so we'll do that one next. And we have a current source conducting 9 milliamps in parallel with a resistor of 2.2 kiloohms, and there's a diode from the upper part of the resistor, and that's got on its anode a 12 kiloohm resistor, and in parallel with that is a current source of, they're connected, of 2 milliamps going upwards. Now if you're feeling on the ball, you might go, I'll do a transformation. I'll transform this Norton source and this Norton source into 2 Thevenin sources. That's fine. That works quite well. I don't know what we do in the answers. We didn't do that in the answers. We might look at it afterwards, but there really is no need to do that. I mean, you can if you want to, but we may as well just carry on with the question as it is. I don't think it will be very much faster to do a transformation, so we'll do the same thing that we always do. We'll say, I assume the diode is not conducting, and rub it out. And then I'll try and find out what the voltage is across the open circuit that's been left by the diode, by the diode being taken away. And the first thing I can do is when I say there is no current from here getting over here, and the reason is the only pathway between these elements and these elements is across the bottom. But one pathway isn't enough. To have a circuit, you've got to have a mechanism for current to flow from this side to this side and then back from this side to this side. At the moment we've only got one because we've taken this away. So we can treat this circuit as if it's 2 different circuits, one over here and one over there. And this is very, very, it's almost trivial now really. We can say, well, looking at the 9 milliamp current source, I've got some current going around like that, and that would be 9 milliamps, must be. Nowhere else for the current to go. So that means that there's a current in there which is 9 milliamps, and in there, and in there, and in there, and in there, and in there. And they're all 9 milliamps. So I've got 9 milliamps flowing through 2.2 kiloohms, and the voltage I'm going to get is going to be in that direction because it's opposing the current. So 9 milliamps and 2.2 kiloohms, well, if we apply Ohm's law, we'll have V is equal to I times R, which is 9E minus 3 times 2.2E3, go. 19.8 volts, so we'll have 9 milliamps times 2.2 kiloohms is 19.8 volts. So I've got 19.8 there, and if we assume that all this stuff here, all this business around here, all of everything there here, this is all my reference, I've got 19.8 volts more on this node here, 19.8 on that, above this reference node. So I could, if I wanted to, just write 19.8 up there, but I'd rather not do that. I'd rather put the arrow on. So we can do the same thing over here. We'll have 2 milliamps flowing into 12 kiloohms, and the current is going that way, and it's 2 milliamps. So we'll have 2 milliamps, 2 milliamps, 2 milliamps, 2 milliamps, 2 milliamps, 2 milliamps. And that will yield a voltage across the resistor in that direction. So it's current through, voltage across, always. And we'll have to use Ohm's law again, and we'll say that V is I times R, and that's 2 milliamps times 12 kiloohms. Well, 2 12s are 24, so 24 volts. There's a 10 raised to the minus 3 here, and there's a 10 raised to the plus 3 here. So you could say, to do this line, is 2 times 10 raised minus 3 times 12 times 10 raised plus 3. And then you go, well, look, that and that cancel, so I've got 2 12s is 24. It's entirely up to you. The only difficulty is, if you start writing it out like this and you forget what the units are, you can end up with megavolts when you want millivolts and all sorts. But it certainly does save a lot of time. So we've got 24 volts across here. Well, that means I know my V anode to cathode now. It's going to be 24 minus 19.8. So which is 4.2 volts. So is more than 0.7, so if it was on the script you might even go is more than 0.7, just to let the poor person who has to mark your exam script know what it is you're thinking. And then we have to do the same thing we always do at this point. Change the circuit so the diode's in it, assume 0.7 volts because that's, well, we don't assume it, we know it's conducting, and if it's conducting we know that we're 0.7 volts across it. And then we'll redo the calculations. So we can, I think I'll redraw it. Yeah, I'll redraw it. And that was 12k, and this was 2.2k. And we now know that this is now, it depends how you feel about this. You can either write 0.7 in there and just remember that it's a voltage source. But if you don't feel happy with that, you can say, well, now I know this diode's on, conducting, I'm going to replace it with a voltage source of 0.7 volts. So if you want to, And I recommend that certainly in the beginning you do, because it makes you think this is a source as opposed to this is a diode. And sources you're happy with, and diodes maybe are a bit of a mystery still. So 0.7 volts. And that's, anode is the more positive, cathode is the more negative. So this represents this diode. So then we have to do our circuit analysis again, and this time it's not quite as simple as saying, well, it's all coupled, it's all decoupled from each other, because there's the two sides of the circuit, and now actually there is a mechanism for current to flow. So we will have to start somewhere, and for consistency I will do it the same way it's done in the answers. You can use any method you like to solve these, but if I give you more than one method it could be tricky. So what we'll do is we'll do it by superposition, and we'll start with the 9 milliamp source. So if I'm going to do this by superposition, I've got to switch off all of the sources that I'm not interested in, and then I'm going to concentrate on one only. Find out what the circuit's up to, and then I'm going to switch that one off and move on to the next one, and then I'm going to find out what the circuit does with that source on, and then I'm going to switch that one off and move on to the next one and do the same until I run out of sources, and then I'll add up the contribution in current to the pathway that I'm interested in, and we'll see what the effect of all the sources are as if they were all on together. So we'll start with the 9 milliamp source, and because this is, or rather, we'll start with the 9 milliamp source, and therefore we will switch off the 0.7 volt source and the 2 milliamp current source. Now, because this is a voltage source, we have to replace it, well, because we are switching this source off, we have to replace it with its internal resistance, and because this is a voltage source, that is 0 ohms. So that's going away, and in its place goes 0 ohms, which is a straight line. Similarly, we're switching off the 2 milliamp current source, and because it's a current source, its internal resistance is infinite. So we will replace that with an infinite resistance, which is an open circuit. And that leaves us with 2 resistors in parallel, which isn't nearly as challenging as 3 sources and 2 resistors. So we can say, well, look, what we want to know about is the current that's flowing in this branch, because this is the branch where the diode is. So we can't just add up, well, not add up, you don't add them up. You can't parallel up these 2 resistors and then work out what the current is, because that would be the current here. That would be the total current leaving the 9 milliamp source, 9 milliamps by the way. So what we've got to do is say 9 milliamps is shared out between this resistor and this resistor, and the share that the 2.2k gets will go down there, and the share that the 12k gets will keep going and go down there. So this bit here must be 9, but that will be a fraction of 9, and this one will be a fraction of 9 as well, and it will be divided up in the ratio of the resistances. So more current will go through the 2.2k because it's the smaller resistor. So if you were to think of current as being water and the resistors as being constrictions in pipe work, this would be a wider pipe than this one. So this gets the bigger share of the current. In fact, we can work it out and say, well, we've got 9 milliamps times 12k I'm going to do it in kiloohms again, kiloohms and milliamps, over 2.2k plus 12k. So that's k as well, isn't it? There we go. That's an omega symbol there. And then you're thinking, well, I'm doing this resistor here, the 2.2k, but I've got the 12k on top. Isn't that a mistake? It's not a mistake. This formula is the current divider formula, and it's in the lecture slides quite early on, lecture 1 or 2. I said this gets the lion's share, the biggest share of the current, and I've got the bigger value on top. If I made this 2.2k, this whole fraction would have a smaller value. So one of the things you have to remember with the current sharing, so our current divider circuit, is that if you want to know about this resistor, you've got to use that resistor's value on top. So if we pop that into a calculator, we'd have 12 over 12 plus 2, 0.2, 12 over 12 plus 2.2 is 0.845 something or other, times 9, 7.6056 milliamps. Does that round up? Yeah. The next digit is a 3, so I'm not rounding that up. Okay, well, that's that current there. Don't care about that current, not interested. The current I'm interested in is the current in the diode, which is now replaced by this short circuit, which formerly was a battery, which represented our switched on diode. So, okay, well I've got 9 and I've got 7 down here, so everything else must be going that way, so I can just subtract this value from this value, and I ought to end up with what my diode current is. So we'll have 9 minus 7.6056, 1.3944. So for my current here, I've got 1.3944 milliamps. That's fine. Now we've got to carry on and do the next one as well. We've got to do the next source. So I'll pop this in the top corner. We'll have ID due to 9 milliamps is 1.3944. And the other thing we've got to remember is what direction it goes in. Now, it's up to you, but I would say that the current flowing in the diode that's positive as far as I'm concerned, because this represents an anode to cathode current for a forward biased diode. And we know this diode's switched on, which means it's forward biased, so we know that ultimately we must find a current that's going that way and has a positive sign. So I'm going to call this minus, and that's a decision I've made. If you want to call this plus, that's fine. But if later you find for one of your other sources a current that goes that way, you cannot call that plus as well. That one will have to be minus. It's your choice as to which is plus and minus, but generally speaking, I like to say, well, I'm going to use the diode to decide what my plus and minus is. So I'm going to call that minus 1.3944. And you could say, well look, the 9 milliamps goes that way, it's clearly plus. It doesn't matter about the 9 milliamps, that's not what's important. It's a question of how the current, what direction the current's going with respect to what you're calling positive current in the diode. And it's in the diode that's the key bit. So, minus 1.3944 milliamps. So then we have to go on to the next source. So I know that when I switch this off, it will go open circuit because it's got infinite internal impedance. So I know it's going away, so I can rub it out now, and I can get rid of all these current lines as well. And we'll do the other current source next, I think. It doesn't matter what order you do the superposition in. This was 2 milliamps, wasn't it? 2 milliamps, yeah. And there's a battery here, but it's still short-circuited because it's still switched off. And this current source, which is here, is open circuited because it's switched off as well. So this is the same problem, but the other way round. We're now looking for a current that's going that way, because some current will leave here and do that, and some other current will leave there and do that. And we're looking for a current going that way. So we know that the current in here and the current in here have to add up to 2 milliamps. So by the same logic as before, I'm interested in this current, which is this resistance. So if I want to know about this resistance, I'll use this value. If you prefer, you can use that one and subtract, because you'd end up with that current there. That will be fine as well. But we'll use this one. We'll say it's 2 milliamps times 12k divided by 2.2k plus 12k. And you're thinking, well, that's the same formula you had before. It's kind of magic that's going on. Before, I worked out the current in here, and then I subtracted the current in here from the total to get the current that went that way. On this occasion, I'm calculating this current directly. So if you wanted to, you could put 2.2 there and then subtract the answer you get from 2 milliamps, and that'd be fine. But I'm not going to do that. And this will give us 12e minus 3, sorry, 12e plus 3 divided by 2.2e3 plus 12e3, 0.84507, which is the same we had before, times 2 milliamps is 1.6901 milliamps. So we have 1.6901 milliamps. Now, this current has the same direction as the current that I'm interested in, and the opposite direction to the prior current that we calculated for the source that was over here. So this one, by my system of current arrows, is positive. So 1.6901 milliamps is positive. So I've got ID due to the 2 milliamp source is plus, but I don't have to write plus because we assume plus if it doesn't say minus, 1.6901. How does it round? It rounds down because the next digit is a 4, which means it doesn't round up. So milliamps. Sorry, it's not a very good M. Milliamps, there we go. So now we've got to do the 0.7 volt source as well. So we'll delete the red stuff. and we need to put diode in that voltage source in there. We'll put in our voltage source, and this current source needs to go away as well, because we're going to switch it off, and that means it'll go open circuit because its internal impedance is infinite. And this has 0.7 volts across it in that direction. But we know that because this is the big one. You can put a plus there if you really want to. So I shan't put an arrow because I don't usually. That's 2.2k. So well, in this case it's a nice circuit with two resistors, and what we really want is the current that's leaving here. And I've made my decision about what that current's up to based on the fact that I know this is the more positive voltage, and I know that this is a source, and in sources the voltage and the current has to go in face the same direction. And if I were to leave my arrow in, my arrow for this voltage would be that way. So we're all right there. We've obeyed the circuit laws properly. So then we've just got to work out what the current is. Well, this resistor and this resistor are actually in series with each other, and they're both then in parallel with this resistor. So we can write without having to do too much too many intermediary equations. We can just look at it and by inspection go, well, look, it's Ohm's law. We've got I is V upon R. This is my total resistance. That's my total voltage. So it's 0.7 volts upon 12 plus 2.2 kiloohms. Obviously, is 0.7 divided by 12 plus 2.2. Brackets around the 12 and the 2.2, and that's 49.2957 microamps. 49.2957, so the 5 rounds up to a 6. But I had more digits than that. 49.29577, so it's 49.2958, because the 7 in the next place causes that to be rounded. And it's microamps. Righto. Well, then I can write that up. And the only thing I've got to worry about, of course, is the other way. So from this one, this is minus as far as our signing is concerned. So ID due to the 0.7 volt source is minus 49.2958 microamps. So then I've just got to add up my three values, and I do just add them. The reason I just add them is because I've already got the minus signs in place, and that's why it's so important to make sure you get your signs right, because otherwise you'll be adding up currents that actually should be subtracted from each other. So we can get rid of the circuit now. We don't need to see that anymore. And we'll do ID total is brackets minus 1.3944 milliamps plus 1.6901 milliamps plus minus 49.2958 microamps is. So I really have added all these, it's just the minus signs are in the brackets, and the brackets aren't really necessary, it's just there to show where the signage actually comes from. So we've got minus 1.3944 E minus 3 plus 1.6901 E minus 3 plus brackets minus Did I do minus in the beginning? I did, yes. Just making sure I put a minus sign in the beginning. Minus 49.2958 E minus 6, close brackets, equals. And I've got 246.4042 microamps. 200 what? 246.4042 microamps. And you notice there is no minus sign here. There is no, sorry, there is now. There is no minus sign just there. So that means this current is going that way through the diode. If there was a minus sign, it would mean that way. And we know that's the case because that's the decision we made about how our currents are being described in terms of direction of positive and negative. So is that the right answer? Yes, it is actually. It's lucky, isn't it? The answer on the sheet is 3.5 volts over 14.2 kiloohms. Yields 246 microamps. So, oh yes, and it says underneath that if you do the conversion of the problem into a Thevenin problem, where you get rid of both the Norton sources and make them into Thevenin sources instead by doing a transformation, as was, I think I was told about it in the first lecture, but otherwise it's in EEE117. Then you can do it much more simply. But it's nice to see a full solution anyway. So, there we are. So parts F and G of question 1 don't actually have any answers in the answer sheet, and the reason for that is the one that I gave earlier, where I said that some of these are meant to be done only by you and not to have answers, in order that you won't know what decision to make as to whether it's conducting or not. Now, I would prefer it if, irrespective of what the question says, you just assume outright it's not conducting and work from there, because that's a nice consistent way to work, and you always do the problem the same way, so whenever you practice the problem, you practice in the same techniques over and over, and that's what really makes them stick in your head. It's not a case that you can sort of have a couple of goes at this and pick it up. It takes practice over and over and over. It's like learning to play a musical instrument or learning to play a sport or something. It's a skill that you have to acquire through practice. So we'll move on to question 2 now,